All right, it's 4 o'clock. Let's go and get started. Good afternoon, everyone. How's everyone doing today? Been good, hanging in there. All right, end of week 10, and so we're in the double digits now. So we're kind of approaching the end, almost November. Okay. So the plan for today, we're going to discuss the requirements for the final project. So I just posted a document onto the Canvas site. I didn't make an assignment for it, so I'll kind of show you where to find it. But basically, we're going to talk about the requirements for the final project, what you're going to be expected to do, and I think more importantly, I think you guys should start thinking about the topic that you want to study, as well as form your groups. Okay, so we'll talk about all that today, and then after that, we're going to move on to continuing our lecture notes on human motion kinematics. Okay. Okay. That's about it. Remember, homework 4 is due this week, so make sure you guys are working on that. Homework 5, I'm getting ready for you guys as well, so that should be posted before the week is done. So I'm hoping to get it out there by. Okay. All right. Any questions on anything before we get started for today? Okay. All right. So let me go ahead. And share my screen here so that everyone on Zoom can see as well. Okay. All right. So here are the final project specifications. Oh, by the way, can everyone on Zoom hear me okay? I think the mic in here is still broken, so I'm still using my mic. Okay, good. Awesome. Okay. So this document was just posted on Canvas, and so if you are not sure where to find it, you can find it from the Files tab. So from our homepage here, go ahead and click Files, and then I've just created a new folder called Project, and then under Project will be this document here. Okay, so I just posted at 3 o'clock today. Okay, and so this document here, it kind of outlines the the requirements and the specifications for the final project. Okay, so let's introduce the project first. And so I might have mentioned this a couple times in class, but the idea with this project is to basically take kind of a more specialized topic within biomechanics. And so, because I know a lot of you are coming in with kind of interest in specific areas, so things like prosthetics, things like sports biomechanics, things like that. Okay, and I want you guys to study that topic, and then I want you to basically prepare a lesson and basically prepare a report on that topic to teach the class. Okay, but I think the important things for this project is to you're going to be doing it's not just a book report. So I don't want you guys to think that this is just something that you're going to watch a YouTube video on it and then you're just going to parrot the YouTube video. Okay, and so I really want you guys to do basically some primary research. So part of the project is actually looking into the scientific literature, going to Google Scholar, searching up some papers on this, and then incorporating that into your lesson, incorporating that into your report. Okay. Not only that, but I want you to incorporate a lot of the techniques and a lot of the lessons that we've learned in the class as well. Okay, and so a big part of the class is to take whatever your area of interest is, whatever your project topic is, and actually do some calculations. So you can either do static calculations, you can do dynamic calculations, basically whatever is most appropriate for your project. Because every project's going to be a little bit different. But that's essentially the spirit of the project, is that you're going to prepare a lesson, you're going to present that in the final week of the course, so that'll be week 16, and then you're going to write a report that cites all this primary literature, that does all these biomechanical calculations, and then kind of put it all together. Okay, and so let's talk about the requirements. Okay. So I've kind of split the requirements up into different sections to kind of make it a little bit easier for you to handle, right? But just keep in mind that every project topic is quite different from each other, right? And so even the suggested topics that I have at the end, there's some pretty significant differences. And so what I've given you here in terms of requirements is just kind of the bare bones, or just kind of the bare minimum. But just know that for each specific project, I'm expecting you to kind of add a bit more as it is appropriate for these sections. Okay, so let's start with the introduction. So first thing you should always do in any kind of scientific report is to introduce whatever topic that you're going to talk about. Okay, and so I want you to describe what your topic is, in general, explain how it's related to biomechanics, and most importantly, explain why it's important. Okay. And so, like I mentioned, a big part of this project is to look into the scientific literature. And so I want you to look at a topic that, that people are kind of still interested in looking into today. And so you should be able to find some scientific papers that have been published, within the last, let's say 10 years, right? And so it shouldn't be something that's already kind of, figured out. Okay. And so I want you to explain kind of why it's important and why people are still studying this, and why, a good understanding of this topic is, can lead to important conclusions in the future. Okay. And so a good introduction should take your topic and place it within context of everything else that we're doing in the class, right? And so this is something that I really want to stress, is that, this is not kind of its own thing. I want you to kind of take everything that we've learned in the class and synthesize that together with your topic. Okay. And so whenever you can kind of draw parallels or draw, connections to whatever you're studying, to, the topics and the lessons that we've learned in the class, the calculations, the analysis, the concepts, I want you guys to do that. Okay. And, and to kind of make it more clear, you can kind of refer to kind of the specific sections of the course that refer to your topic. Okay. All right. And so, the final thing that I'll talk about in the introduction is that, ideally, if someone else were to read your, read about your topic from your reports, or listen to your introduction from the presentation, they should come away with the sense of, this is something that's really important to know, and this is something that's really relevant to biomechanics and relevant to kind of everything that we've been studying in this class. Okay. Okay. Next section is on the biomechanical analysis. So this is probably one of the biggest sections that you're going to have in the report. Okay. And so throughout this class, we've learned a lot of different techniques for computing things like muscle forces, joint reaction forces. Next we're going to go into some techniques in terms of how to track motion, and then again kind of relate that to muscle forces and joint reaction forces. And so I want you to do those same kind of calculations, as part of your project, right? You can almost think of this as like, if I were to tell you that, maybe God forbid, maybe I get hit by a car in the last week of class, and I need someone to write a homework assignment for everyone to do, right? And so, I want you guys to write those homework problems based on your topic, okay? And so, write the problems as if it was in the same style, as the homework problems as I give you, as the example problems that we did in the class, so on and so forth, okay? And so, of course, because of the techniques that we're learning in this class is, we often have to simplify the geometry or make assumptions based on, what muscles are acting. You'll probably have to make those assumptions as well. Okay. And so feel free to make those assumptions to make the analysis easier. Okay. And so, again, look at the example problems, look at the homework problems, to kind of get a sense of, how do we take kind of a physical kind of biomechanical system of a living person, and then simplify it in a way that's actually, it's actually practical to do calculations on. Okay, so you might have to simplify geometries, you may have to simplify forces and things like that. Okay, and so at the very least, you should have free body diagrams. And so if you're going to be doing static analysis, and so that's a very common one that's done for this project. Make sure you have your free body diagrams. Make sure you have your equations of motion. Make sure you show me the work that actually goes into solving these problems. Okay, again, it's like you're writing your own example problems. You're writing your own homework problems. For the final project. Okay. And so, you're also going to need to do things like justify your assumptions, justify your the locations of your loads, and things like that. Okay, so for your final report, you should have at least 5 biomechanical analyses. Okay, so I'm expecting basically 5 separate problems in your final report. You're not going to have to present all of them in the final presentation, just because we are time limited in the final presentation. So you should expect to present at least 2 in your presentation. Okay. So 5 total, but you only need to present 2 for your final presentation. Okay. You're welcome to present more for your final presentation, but you're also going to be limited in terms of time. Okay, so that's kind of the main section of the report. The next section is the discussion section. And so this is a pretty standard section for most scientific reports. And so you can think of your of the previous section as kind of been like your experimental data or your experimental analysis. Okay. And then, so, the thing that usually comes after that in a paper like this is to take those results, take those numbers, and discuss them and analyze them and kind of talk about how those numbers are either significant or not significant, relevant or not relevant to kind of the what you want to discuss. Okay. And so, of course, I'm the way I'm describing this discussion section, it's very broad because, again, exactly what you discuss and kind of what numbers are important and what data is important is going to depend on your specific project. Okay. But I do want to see some kind of analysis in your report. So it shouldn't just be the calculations, and then I shouldn't just see 5 calculations in your report, and then that's it, right? And so you should be able to discuss, and you should be able to talk about why these discussions are relevant. Okay. And so, for example, one topic that's actually very popular every year is to do a biomechanical analysis of an animal, so something besides a human, right? And so, geometrically, anatomically, animals are quite different than humans. So when you compute things like the muscle forces inside a cat, something like that, right? A cat that's like jumping up on a bookshelf, they're going to be quite different. And then, relative to the amount of weight that a cat has, relative to its requirements in terms of how fast it needs to move, how nimble it needs to be. Those numbers mean something. That they're not just numbers on their own. And so I want you to take those numbers, put them in context in terms of what's important for your project, and discuss that, analyze that in your report, analyze that in your presentation. Okay. And so I gave you some kind of example discussion points here. Okay. And so, another very common topic is to do a project on kind of sports performance. And so, you can compare like the performance of a top athlete, maybe a top sprinter, maybe to what a typical human would be able to output in terms of their muscle forces and walking speeds and things like that. Okay. All right. And so the last aspect that I want to talk about is your sources. Okay. And so this is going to be an important part. And so I expect everyone to to do quite a bit of research for this topic. And so I want you to have at least 12 different sources overall. Okay. 4 of those need to be from a scientific journal, right? And so that's basically primary research. So you're going to go to Google Scholar, and I want 4 articles from there, and I want those to be to factor into your report. Okay. And so you may get lucky. Maybe you choose a topic where you find a scientific paper that does a lot of these calculations, and so they kind of give you a framework in which you to do it. And so if you find that's great. Okay. And so you're able to find a paper that kind of does those calculations and puts it within the context of the class. That's very useful. Sometimes you're not going to be lucky, and so maybe you don't. Maybe you find papers that has data but doesn't show you the work for those calculations. But I do want at least 4 primary sources. And so I did increase that relative to last year. So last year was only 3. What I was finding last year was I had most people worked in groups of 4, and what I found was that one person kind of got off the hook because with groups of 4 and only 3 primary sources, there's always one person, at least one person per group, that got away with not having to do any kind of primary research. And so I increased that to 4 this year, so that everyone in the group has to at least find one article and bring that to the table and factor that into the project. Okay. Okay. And if you you can also source textbooks as well. So textbooks are totally fine. And if you're not sure about a source, about its legitimacy, you can run it by me, and then we can we can see if it's legit or not. Okay. Okay. So that's a summary of all the requirements. Any questions on this so far? Okay. Okay, deliverables. And so I've kind of already mentioned this, but there are 2 kind of things that you're going to turn in for this project. And so the first thing is going to be the final presentation. And so the final presentation is going to take place with the entire last week of lectures. So we're going to have half the groups go on Monday. We're going to have half the groups go on Wednesday. Okay. And so you can think of the presentations as being kind of a brief summary of the contents of your report. And so usually the presentations are around 12 to 15 minutes. And in fact, we can't really have them go beyond 15 minutes. Otherwise, we're not going to have enough time for everyone. Okay. So it is expected that each group member is going to participate in the final presentation. So every group member should expect to speak, and they should speak roughly about the same amounts. Okay. And so, of course, the final presentations are going to be given kind of a week and a half before the actual project is due. And so, I don't expect you to have everything done at that point, but you should have enough to present in like a 15-minute presentation. Okay. And I'll give you a rubric at a later date to kind of show you kind of exactly what I'm looking for. All right, question in the chat. So is 4 scientific articles a minimum? Could all 12 be scientific articles? Absolutely, yeah. And so if you want all 12 of your sources to be scientific articles, that's even better. And so, 12 sources overall, but only 4 of them have to be from scientific articles. The rest can be like, web articles, maybe from a reputable source. Maybe they are lectures, a video lecture, maybe they're a chapter in a textbook. But only 4 of them have to be articles, but you can do more, of course, as well. Okay. And then the other deliverable, of course, is going to be your final report. So the final report, it does have more content than what's going to be in your presentation. Okay. And it should have all of the required components above. Okay. And so this part's important. And so, and so I know that, whenever you have a group project, each person in your group is probably going to be responsible for different components of the report. That's kind of naturally kind of what makes the most sense for a group project like this. But I don't want the final report just to be like a copy and paste of everyone's parts and just kind of put it all together in one. Okay. There should be some cohesion between the sections. Okay. And there should be, some proofreading that goes on, it doesn't have to all have the same style. It doesn't have to all have the same kind of, voice and things like that. But, what I kind of see the most common is that, people write different sections of the report, and then different people kind of write the same things, and then you just kind of copy and paste them together. So I'm kind of reading the same thing twice, just, with a different person explaining it. And so, I do want at least one person in the group to go through and edit the whole report to make sure it flows nicely, make sure there's nothing repeated and things like that. Okay. And keep in mind, and so that editing does take a lot of work. So, don't leave that all to one person. If you're going to leave that to one person, make sure you kind of compensate and make sure that, other people are kind of picking up the slack elsewhere. Okay. Because editing a group project like this is not easy. So if you've never done it before, it does take a lot of work to kind of synthesize everyone's contributions. And so, but I do want that to be part of I do want kind of a good cohesive report. Not just, if I wanted 4 individual reports, I would just have this be an individual project. So, I want you guys to kind of work together and make sure that the final deliverable is kind of something nice, something that you can actually present and kind of be proud of that. Okay. All right. So just like the final presentation, I'm going to release a rubric. The rubric's not going to change too much from last year, and so I just need to upload it, just make some small changes. Okay. And the final due date for everything. So for the final report, that's the last thing you're going to turn in. That's going to be due on Monday, December 18th. Okay. And so if you, if you look at this date right here, you'll see that this is actually the Monday after finals week. Just because I know during finals week, a lot of you guys are really busy studying for exams, doing exams, finishing other projects. And so, I wanted to give you guys a little bit extra time to make sure that you can finish absolutely everything. So that's why I have it due the Monday after finals week. But I can't really push it beyond that, because I do need to finish grading everything and post grades before Christmas. And so to make sure I have time to read every project from this class, every project from all my other classes, I have the cutoff the Monday, December 18th. And I can't really be flexible with that, because it's, otherwise then I don't get to see my family for Christmas, which is, well, could be good for some reasons. I don't have to see my crazy auntie, but generally I want to see most of my family for Christmas. So, so please try to turn it in by Monday, December 18th. Okay. Final project, final report components. And so I'm going to give you a template for the final report. And so it's going to give you all of these sections. And so, you can just kind of follow that template. But please do use these sections, because I do use them to kind of to grade your final report. And so if everything is sorted out into the particular sections, then it makes it kind of easier for me to grade it. Okay. Okay. And so probably the most common question I get for these kinds of projects. And so, there's no page requirement. And so I don't have a minimum on the page count, and there's no maximum, so you can use as many pages as you want. But if you want kind of an approximate ballpark, so I'd say most projects for this class, with all of the calculations and all the figures and all the description stuff, they usually are kind of in the ballpark of 18 to 25 pages. I've had reports that go beyond that. I've had a 50-page report before, which was great. They did a lot of hard work on that project, but it was kind of a lot to go through. But most groups kind of end up in this range right here, 18 to 25. Okay, and so that includes figures, of course. Okay, and so and speaking of figures, your report should have liberal use of lots of figures, tables, and pictures. Not only to substantiate a lot of the maybe the discussion or maybe the introduction, but I think more importantly, for your calculations, I want to see things like free body diagrams. I want to see things like where the forces are acting, things like that. Okay. Okay. Teams. And so this is a team project, and so this is something that you're going to work together with other people in the class. And so the group size is 4. And so I don't want to go beyond 4 students. And so make sure you find a group of 4. Okay, you could have less students, and so it is possible to do maybe 2 or 3 students. I don't want to do any solo projects because we're not going to have enough time for the presentations at the end. And so you should expect to at least pair up and maybe work with a group of 3 for the project. 4 would be ideal. So if you could find 4 students that are willing to work on the same project, that is the best. Okay, but I definitely don't want to go beyond 4. Otherwise, it's kind of hard to coordinate. It's kind of hard to get everyone's contributions onto the project. Okay. Okay. All right. And so so that's the project. And so the last thing I'm going to do today is kind of talk about some suggested topics. You don't have to follow these topics here, but these are kind of what people have generally worked on in the past, and then they're available for you this semester as well. Okay. But before we do that, are there just any questions on the requirements or the deadlines or kind of anything for the final project? Okay. Okay, so let's talk about some potential topics. So these are just some suggestions. And so you don't have to choose one of these categories. In fact, I have an 8th category here where you can run a topic by me. I know some of the grad students are already thinking about their topics just because they've already sent me their graduate project or graduate extra assignment. And so you feel free to not have to stick to these. Okay, but I think it's helpful to kind of get a sense in terms of what other people have done and kind of what I'm expecting for this project. Okay, so the topic 1 is sports performance. So we can have multiple different groups for this. And so, one, I think topic that's really interesting is to see is that, when you're talking about kind of a competitive sport or a sport just in general, those athletes kind of have to train their bodies in a particular way to make sure that they can perform well in their sport. Okay. And usually what happens is that in these sports, there are 3 or 4 or 5 different motions or different techniques that are really important for optimal performance. Okay, and so you can pick a sport and you can analyze what are what are these techniques, what kinds of muscle forces are involved, what is required of a top athlete versus kind of a normal person. Okay, and so this is a pretty popular topic, and at this point, this is the 3rd time I've taught this class. I think I've had groups that have covered almost every sport under the sun, and so people did soccer, basketball. Actually, no one's on baseball yet. Now I think about it. Swimming, soccer twice, and so I've had a soccer group every year, and so so if you're gonna I'm not going to stop you from picking soccer, but I have seen soccer several times. I've seen Lionel Messi kick a ball in a report many times at this point. So and so you can do it, but just know that I've seen it a few times before. Roller skating, roller skating would be a really interesting one. That would be really cool because the biomechanics that go into roller skating I think is quite different. So that's definitely a good topic and one that's quite popular. Okay. All right, number 2, animal locomotion. So this again can have multiple groups just because there's just lots of different animals in the world. And so I think one thing that's really interesting because we focus mostly on human motion, the numbers that we've chosen and kind of the geometries and orientations have been for humans, but you can apply these same techniques for animals as well. And so if you want to analyze how a cheetah runs or how a cheetah jumps up on things or how a bear goes fishing, right? And so how much strength that does the bear need to have to break into your SUV when you're going camping, right? And so all of these I think would be really interesting topics for the project, and you're well equipped to do that. And so by the time you do this project, you'll have lots of different analysis techniques for statics, dynamics, to do this kind of analysis. Okay, 3 is surgical reconstructions, and so this is kind of more on the tissue side, more on the conceptual side. And so it happens a lot nowadays where people are injuring, they break their bones, they tear their ligaments, they tear their tendons, and so they have to get surgery to kind of reconstruct that body part. Okay, and so this would be an interesting topic just in terms of what are the considerations that surgeons are going through, what materials do they use to kind of repair these parts. What are the biological processes that are involved in the repair of these tissues? Okay, and what is the kind of quality of life, and what is kind of what are the actions that people can do after they go through a reconstruction? Okay. Number 4, prosthesis design and manufacturing. So prosthetics, I know is kind of a strong topic of interest. And so if you want to do a topic on prostheses, there's a lot of really interesting calculations you can do here. So if you were to have a prosthetic limb, what are kind of its material and geometric properties that are different from a normal limb, and how can we use engineering to kind of mimic a normal limb or even improve a normal limb relative to prosthetics. Okay, number 5. Number 5 is kind of like a bigger topic, so I call it sports equipment or movement equipment, but just any kind of device or any kind of assist device that's used for for either augmenting movement or protecting the human body. That's kind of what you can do here. So there's a lot of different things that you can do in this realm. Okay. All right, 6, biomechanics of weightlifting exercises. So actually, this is actually pretty on the nose for what we've done in the class. So a lot of the examples, a lot of the homework problems that we've done in the class are for weightlifting exercises, and so you can kind of dive deeper into that realm. And so talk a bit more about kind of what are the kind of the strategies and what are the techniques in terms of what gives you the most gain in weightlifting, and what are certain techniques that you can use to to maximize your workouts. Okay, and I think more specifically, what I'm looking for here is to do multiple muscle analysis here. So if you were to do an exercise, use a lot of exercise actually exercise more than one muscle. And so doing that analysis and seeing, what are all the different muscles involved in the different exercises, I think would be really interesting. Okay. Robotics. And so another very interesting topic. And so, I think every day, we're developing robots to kind of, either augment human motion, or to mimic human motion, or improve human motion. Or even do things like, a big area nowadays is called bio-inspired design. So, how do we take inspiration from how, biological animals are do things, and how does that inform how we make robotics or devices in general? Okay. Or another topic, right? And so, and so I think actually, a couple grad students have already kind of reached out to me about ergonomics. And so, how do you design things like the seat of like an airplane or something for a pilot, in order to make it so that that they can continue piloting for 30, 40 years without ruining their back and things like that. And so that would be another really great topic, I think, for the final project as well. Okay. All right. And so any questions on any of these topics? Any of these topics here? Question in the chat. Our question: what is the extra assignment for grad students? Will it be posted soon? Yeah, so the extra assignment for grad students is to do kind of your own individual, literature review. And so, as part of this project, you have to look for at least 4 scientific articles. And so for the grad students, what I want you guys to do is to find, or is to use one of those articles and write your own independent review of that paper, right? And so I don't have anything written up for the graduate assignment, but I do want you to at least look up a few different papers on Google Scholar, run those by me, and I can help you pick one to write a summary or report about. Yeah, so that's the extra assignment for grad students. Okay. All right, question for topic 7: can we analyze multiple bio-inspired robotic systems? Absolutely, yeah. And so, in fact, that's probably going to be helpful because when in order to get up to 5 different calculations, you probably need to analyze several different systems. And so, so absolutely, you can do up to 5 or even more systems if you want, but there should be at least 5 different calculations in the final project. Okay. Any other questions on this? Okay. All right. All right, so that's the final project. So definitely, start thinking about, who you want to work with. Start thinking about kind of the topic that you want to do, and once you do select a topic, have everyone in your group, email me and run it by me because, because sometimes, if you're going to be doing a topic that, I want to make sure that there's enough content there for you to do the project. I want to make sure that it's not, overly complex so that, you're not spending, a disproportionate amount of time. And I think more importantly, I want to make sure that no one in the class is doing the same project. Okay, so I want every group in the class should be working on their own, and on an individual topic, so that once we get to the final week, we'll have 9 to 10 different presentations of 10 different topics. And so but if 4 of those are the same, then it's kind of it kind of gets boring at that point. Okay. Okay. All right. So let me go ahead and stop sharing here. Go ahead and bring back the iPad. Okay. All right. So let's go ahead and pick up where we left off on Monday. Okay. So on Monday we were talking about human motion kinematics. Okay. Specifically, we were talking about optical motion capture. Okay, so let's start there. Okay. So like I mentioned on Monday, optical motion capture is kind of the state-of-the-art way to measure human motion kinematics. And what I mean by that is how do we basically track human motion? How do we quantify it? And how do we describe it? All right. So our end goal with this, and I'm not sure if we're going to get to it today, but basically our end goal is to basically be able to track or to plot, the various joint angles as a function of time. Okay. And so, for example, we saw a few of these plots when we were talking about gate biomechanics, right? And so, for instance, one plot that you might see maybe is the knee flexion angle. Okay. And so that's the flexion angle that's made at the knee joint as a function of time. And let's say maybe during walking. Okay. All right, and so our goal is basically to get a plot like this, and so to basically come up and basically have a system and have the computations and the code in place, so that if you have someone that's walking in your motion capture lab, to be able to track what is the knee flexion angle as a function of time. Okay. All right, so a plot like this, or kind of data that can allow us to plot like this, that's the goal. Okay, and so what we're going to talk about is, how do we, first of all, how do we even get data from optical motion capture, and then how do we kind of process that data through some calculations in order to get data like this. Okay, because from here, what you can do, and so essentially, this basically gives us theta of t. Okay, where theta of t here is the kind of you can almost think of it as like the joint angle as a function of time. Okay. If you take the derivative of this, okay, which you can do, right? You can do that from the data. So all you have to do is take just a finite difference of approximation, okay? And so this, of course, is going to be a function of time. Okay. And so taking the derivative of an angle gives you angular velocity, and you can take one more derivative. Okay. And if you take the derivative of angular velocity, you get angular acceleration. Okay. All of these can be obtained, if you're able to track, the joint angles as a function of time. Okay. And so what we're going to see in the next section, and so probably, hopefully we get to it by Wednesday of next week, is how to take this data on angular position, angular velocity, angular acceleration at the joints, okay? And then we're going to run it through something called inverse dynamics. Okay. Right. Which essentially, essentially all that is just, constructing the equations of motion F is equal to ma, right? Except that acceleration is going to be, determined from these quantities here. Okay, and then ultimately, what this is going to allow us to do is compute, the muscle forces as a function of time, the joint reaction forces as a function of time. Okay. And so we'll be able to track in terms of, how much force or how much work your muscles are doing during this motion. Okay, so that's kind of the strategy. That's kind of the roadmap in terms of what we're hoping to accomplish. Okay, and so that's basically going to take us up all the way to Thanksgiving break, is covering all these topics. Okay, but the first step in all this is getting this plot, getting this data right here, which we usually obtain through motion capture. So that's kind of what we're going to talk about today. Okay. Okay. So that's kind of where we're going with this. Okay. And so if we recall from Monday, the way a motion capture setup works is that, you're going to have someone in a lab. Okay, you're going to surround them with several different cameras, at least two, but more cameras are better. And then you're going to put all these kind of reflective tracking markers on them. Okay. And so the idea is that, those cameras are going to track the positions of those markers as a function of time. And so, you may have someone like this. And then all on, they're going to wear probably a suit where, these things are kind of easy to stick. Okay. Right. And so as a person goes through their motion, the camera's going to pick up these trackers. And, from there, you'll be able to process it and get the joint angles as a function of time. Okay. Okay. So before we actually jump into the calculations in terms of how this works, let's talk about a few practical difficulties that are involved in a setup like this. Okay. All right. So if you recall from Monday, we talked about it. In order to kind of fully track the motion of a body segment, you technically only need 3 markers, right? And so you basically just need to triangulate the position of that segment. Okay. But in practice, you usually need more than 3 markers per segment in order to to track its motion. Okay. And the reason for that has nothing to do with the theory itself. It just has to do with the fact that, as a person kind of goes through its motion, and you're trying to capture the motion of these trackers with the cameras, right? Certain positions of the bodies are going to hide the trackers from the cameras. Okay? And so sometimes right, and so in the event that you lose, you lose sight of a tracker during a motion, and it's kind of an important part of the motion. If you don't have some redundancy in the system, you may lose some data for that particular motion. Okay, so a lot of times extra trackers are added for this reason. Okay, and that's going to be actually very relevant kind of later on once we kind of talk about how these calculations work. Okay. Another thing that can happen is that, as a person kind of goes through your motion, these trackers, are not completely stationary on a person's body, right? What kind of the assumption that a lot of people make is that once you put a marker up, so let's say you attach a marker to your arm, that marker is kind of rigidly there, right? But what tends to happen as a person kind of moves their body is that the local position of these markers tends to move. And so they kind of either shift or kind of vibrate from their original positions. Okay. And the reason for this is that, ultimately, you're attaching these markers on top of, basically on top of their skin, right? And so the skin is a fairly soft tissue. The skin is covering muscle, which is a fairly soft tissue. Depending on the part of the body, that there's going to be some fat tissue in there, which is also soft. And so as a person kind of goes through their motion and the muscles kind of change shape, right? They're going to contract and elongate, right? The fat that's in your skin is going to jiggle as you go through certain motions. And so, sometimes these markers tend to kind of, they're not kind of fully fixed in their positions. Okay. Okay. Which ultimately, is not that, most of the time is not that big a deal. But what it kind of manifests itself is that, or the way it kind of manifests itself is that the data that you get is often very noisy. So it's usually not a clean signal. So you have to kind of filter the signal. You have to process it in order to get it to a point where it's useful. Okay. And so that's particularly relevant because, a lot of times in order to compute things like the velocity and the acceleration, you have to take kind of local derivatives of your signal. If you have kind of spikes or if you have kind of dips, right? If you have kind of a noisy signal, taking derivatives of that noisy signal is going to lead to a lot of errors. And so you want to kind of be careful with that. Okay. Okay. And so the next section that I'm going to talk about is kind of the numbers in terms of the calculations, in terms of how do we actually process this kind of data. Okay. So before we actually get there, are there any questions on this? Okay. Okay. So let's go ahead and move on to the next section, which is called inverse kinematics. In particular, we're gonna cover a particular technique called unconstrained inverse kinematics. Okay. So unconstrained inverse kinematics is basically the process of taking our mocap data, taking our marker positions, and actually converting those to joint angles. Okay. Okay. And so the idea is this, is that, and so using mocap data, okay, what we're going to do is we're going to assign a coordinate system or a reference frame on each rigid segment of a person's body. Okay. And so, for example, I'm gonna give you a 2D, what it would look like in 2D. Okay. And so if you took the arm, for instance, okay. And so here I have 3 segments for the arm. So I have the upper arm, the lower arm, and the hand, right? What we would do is that, using the mocap data, we'd be able to assign, a local coordinate system in each of these segments. Okay? Right? By default, usually we put these coordinate systems in the centroid or the center of mass for the system. Okay? But they also don't have to be. Sometimes you may want to actually put the axes on at a different location. Okay. And so as the person kind of goes about their motion, these coordinate axes are going to stay fixed to that segment and rotate along with that body segment. Okay. And so, for instance, if this were to change, right? And so if we were to kind of, move our body so that, we are kind of in this position here, okay? If we kind of assume that the x-axis kind of points down the length of the long bones in this case, okay? Our 3 coordinate axes would look something like this. Okay. And so the coordinate axes are going to, we're basically going to assume that we're attaching that coordinate axis to the underlying bones in that segment. So they're going to be, basically fixed in their orientation once we kind of establish their kind of resting position. Okay. And then as a person moves, those coordinate systems are also going to rotate. Okay. All right. And so the basically the difference in orientation of successive coordinate axes, that's going to define our joint angles. Okay. All right. So in this case, if we wanted to compute the joint angle at the elbow joint, okay. So this right here is our elbow joint. Okay. So the elbow joint is the joint that joins your upper arm to your lower arm. Okay. the way we do that is we look at kind of the difference in orientation between the x1, y1 coordinate system and the x2, y2 coordinate system. And well, since this is 2D, we can kind of define it as just the angle between x1 and x2. Okay. All right. And so for a 2D case, it kind of seems a little bit overkill just to have kind of a full coordinate system, right? It kind of seems like the y-axis here aren't really doing anything. And so, we can just use the x-axis and determine the angles from there. But remember, human motion is for the vast majority of the time a full three-dimensional motion. And so if you wanted to describe kind of the difference in orientation between two joints, oftentimes you're going to need multiple angles to do that. Okay. And so this theory becomes especially relevant in 3D, where you're not only kind of considering kind of the difference in one plane, but you're also considering the angular rotation relative to the x direction, the y direction, and the z direction. Okay. Okay, so that's the idea, and so basically we're going to basically go over the calculations in terms of if you have two coordinate axes. So the coordinate axes themselves are fairly easy to determine. We'll do an example of that in a bit. But what you'll see is that if you have three reflective markers on a person's segment, right? You can use those three markers to kind of come up with an x, y, and z axis using things like vector subtraction, vector cross products, and things like that. Okay, but that's the basic idea of inverse kinematics, right? So you have markers on the person's body segments. You're going to take those markers to find a coordinate system, sometimes multiple coordinate systems, and then you're going to look and see how the orientations of those coordinate systems change as a function of time, and then that's going to determine your joint angles. Okay. All right. Any questions on this so far? Okay. Okay. And so if you notice, kind of from the title of the segment, we called it unconstrained inverse kinematics, right? And so what the unconstrained means is that we're not going to place any constraints on the lengths of the limbs or any constraints on the joint motion. Okay. Because in reality, each of your limbs is a fixed length, right? And each joint is only capable of certain ranges of motion, right? And so, an elbow joint is only a hinge joint. It's not able to do ball and socket, rotation in all three planes, right? And so, in reality, when you do these calculations, you have to kind of factor in those constraints so that the calculations that you perform are not going to violate any of those rules. Okay. But since it's already kind of going to be kind of a lot of calculations to do, and so we're just going to kind of ignore those constraints and just kind of look at pure unconstrained motion. Okay, and so so whenever we're always going to be comparing the motion of two segments, side by side. We're going to assume that there's going to be no limitations in terms of the motion for those joints, okay? Which is fine. And so there's a lot that we can do here. And in fact, everything that we use in this section is used for the constrained motion as well. Unfortunately, we're not going to be able to cover the constrained motion in the class just due to the time constraints of the course. But just know that state of the art, you do have to factor in those constraints. Okay. Okay. Okay, so the next point I want to make here is that, when we do, define these coordinate systems, technically speaking, we want to attach those systems onto the underlying bones inside that body segment. Okay. Because in any given body segment, the bones are the most rigid part of that segment. Okay. Because like we talked about earlier, the muscle tissue, the skin tissue, the fat tissue, all of those can kind of wobble and wiggle and kind of change its shape. Okay? And so if we want to get a true measure of the joint angles for a person's motion, we should ideally attach our coordinate systems or do our tracking according to the bones. Okay. There's one problem with this though, and so that sounds great, right? And so that sounds great in theory because you should track the motion based on whatever's most rigid, whatever's going to be most consistent. Okay. The problem is, your bones are inside your body, right? And so it's with a few exceptions, right? There are some exceptions where your bone kind of comes close to your skin. Okay. It's going to be impossible to actually place markers directly onto the bones. Okay. Okay. Not only that, but if you were to attach markers that kind of correspond to maybe the full length of your arm, the locations of those markers are kind of an inconvenient location, so they're not easily tracked by cameras. Okay. For instance, and so one tracker that's used for your elbow quite a lot is that you can kind of feel it, and so it's kind of on the inside of your arm, right? So if you kind of feel on the inside of your arm, there's your humerus bone kind of sticks out a little bit at your elbow joint, right? So the inside of your elbow, where that bone kind of comes out right there, that would be the perfect place to put one of these markers to track the motion of your humerus. Okay? But because that location is kind of on the inside of your body, right? Unless you're doing a motion where you're kind of waving your arms in the air quite a lot, that's going to be hidden from cameras, maybe 90% of the time because your arm is going to be close to your body. Okay. And so the locations where the bony landmarks are just not easy to track with cameras a lot of the time. So it's maybe you might get one, but then you maybe not track all three that you need. Okay. Okay. And so to alleviate this problem, we kind of use a kind of a two system, a two coordinate system. Okay. And so what you're going to see is that actually, we define two coordinate systems per body segment. Okay, we have one coordinate system that is attached to the bones. Okay, and so we place the markers in strategic locations where we're at least reasonably speaking, we're able to track the motion of the bone underneath. Okay, so that's one coordinate system. The other coordinate system is one where you place the markers in locations where it's easy to track from the canvas. Okay. Okay, so per segment, we're going to have two coordinate systems. Okay. All right, and then I'll draw a picture for you kind of soon after this. Okay. All right, so the first coordinate system, this is the one that we actually use to compute joint angles. We call this the anatomical reference frame. And so the idea with the anatomical reference frame is that this is the reference frame that's basically attached to the underlying bones. Okay. And so, usually this involves placing markers, all the way up and down the body segment. And they're positioned in a way so that, whatever axis that we choose, usually it's the x-axis. The x-axis, will align with kind of the axis of the long bone. Okay. Right, so I want to stress that the anatomical reference frame, these are the ones that are actually used to compute the joint angles. Okay, because ideally, these are the ones that are attached to the bones, which is kind of the direction of orientation of the body segment itself. Okay, and so if we look at the anatomical reference frame for both, for two adjacent segments, and we compute the difference in their orientation, that's going to give us the joint angles. Okay. All right, but because these these are often the way that we the way that we define these based on where the markers are, these are usually, the anatomical reference frame is usually difficult to track in real time. So you may get there may be certain poses or certain positions of the body where you can actually see all three markers that are used for this for this reference frame, but you can't often rely on that. So there'll definitely be frames where you don't see all three markers, and from there you kind of lose the anatomical reference frame. Okay. All right, so to alleviate this, we define a second reference frame for each segment, which we call the tracking reference frame. All right, so the tracking reference frame, again, this is going to use three markers. Okay, so you're going to have three markers for the anatomical reference frame, three markers for the tracking reference frame. But the markers for the tracking reference frame are placed in locations that are going to be easy to track. So they're going to be on the exterior of the body. They're not going to be covered by the body under, at least under most circumstances. And so these are usually easy to track in real time. Okay. And so even though these markers here are easy to track, they're placed in locations that don't correspond to the underlying bones. And so these ones are not used to compute joint angles. Okay. So let me draw an example for you of kind of what these look like, just because, from the descriptions, it's a little bit hard to visualize. And so let me show you kind of what it would look like if we were to do mocap on the leg. Okay. Okay. All right, and so I'm gonna draw you kind of where the trackers would typically be for, maybe the anatomical reference frame. Okay. And the tracking reference frame. Okay. Keep in mind that when you're doing motion capture, the cameras are always kind of around it, right? And so kind of the best locations for the tracking reference frame is going to be somewhere on the exterior of your body. Okay. Okay. And so so this is from a frontal view. So this is, you're kind of viewing someone's leg from the front. Okay. And so let me go ahead and draw, maybe this will be the thigh. This will be kind of the lower leg here. Okay. Right. So this is kind of one person's leg, where kind of the middle here is the knee. Okay. So we have two body segments here. And so we have kind of the thigh and the lower leg. Right. And so for the anatomical reference frame, you want to place the markers on kind of, locations where it's close to the bones, right? And so they're kind of where the bone's going to come close to the skin. And so for your knee, your knee kind of has a good spot kind of both on the inside of the knee and the outside. Okay. I don't know why I felt the need to touch my knee, because it's still in the same place, but I guess I had to confirm that my knee's not broken, I guess. Okay. Okay, so we have markers kind of on the inside and outside of the knee. Okay, and so those are going to be the ones that are kind of closely going to track, your femur, and also your radius and your not your radius, your tibia and your fibula. Okay. Okay. And then another good location to track the femur is on your hip, and so kind of right on kind of the exterior of the hip. And so, maybe we have one marker that's kind of right there. Okay. Okay, so that would be the three markers that govern your femur. Okay. And then based on these markers, we'd be able to define a coordinate system, maybe that looks something like this. Okay. And so we draw a coordinate. And so you can see here that that if you draw a line from the hip to the outside of your knee, okay, that's pretty closely in line with kind of the direction of the femur. Okay. And so we can make your x-axis kind of parallel to that. And then we can define the directions of the y direction and the z direction based on the third marker, and by taking cross products between these. Okay. All right, same thing for the lower leg. And so, some additional bony landmarks on your lower leg, could be in your ankles, right? And so you feel kind of the inside and outside of your ankle, you'll be able to feel kind of the tibia and the fibula down there. Okay. So in this case, we have kind of an extra marker, so you have kind of more than 3. Okay. And so what you can do from those markers is you can make technically you can make a coordinate system for both the tibia and the fibula, okay, based on those markers. Okay. But these may not be easy to track, especially the markers that have to be placed on the inside of your body. Those may not be that easy to track, because you may have your other body part covering it, or maybe kind of turned away from the camera. Okay. And so the anatomical view might be kind of difficult to track. And so to fix this, we have the tracking coordinate system. Okay. Where we're going to put the markers in kind of very convenient locations. So, maybe we put one marker kind of on top of the thigh, another one there, another one there. Okay. Right. We're going to put that right in the front of the thigh, so that they're much easier to track. And then same thing for the lower leg. So maybe for the lower leg, maybe we put, let's say that the right side here is the exterior, right? And so we put more markers kind of close to the exterior. Okay. Maybe we do something like that. Okay. And so if we define the coordinate axes for these markers, it may look something like, like this. Okay. So they may not necessarily align with kind of the underlying bones, but at least we'll be able to see them throughout the entire motion. Okay. And so in order to kind of properly track the motion during a motion capture setup, we need both of these, okay? And then, of course, we eventually need to relate these guys together, okay? And so eventually what you're going to do, and this is usually done in kind of the beginning stages of the mocap, right? And so if you've ever watched kind of videos of people doing motion capture, what you'll see is that kind of in the beginning, they have to calibrate the machine, right? And so what that basically means that the person kind of stands in a certain position so that all of the markers are visible, okay? Okay. Because from there, if when all markers are visible, you're able to track the positions of every single coordinate system on this person's body, all the anatomical coordinate systems and all the tracking coordinate systems. Okay. And then for each segment, right, for each segment that we're interested in capturing motion for, what we can do then is we can create a way to relate, the tracking coordinate system and the anatomical coordinate system, for that particular segment. Okay. So we need to form a mathematical relationship. We said that, if the tracking coordinate system on this segment is in this position, that means the anatomical coordinate system is in, a different position, okay? And the way that we relate these is we're going to use a mathematical tool called a transformation matrix. Which, if you're in my finite element class, you're going to find hilarious because we literally just finished talking about these last week. And so you thought you escaped transformation matrices, but you're going to see them again in this class. Okay, transformation matrices are useful, and so whenever you need to compute or kind of quantify and track the orientation of two different reference frames, that's kind of the standard way to do. Okay. All right. So, any final questions on this before we wrap it up for the week? Okay, all right. So when we come back on Monday, we'll talk about the mathematics of the transformation matrix. We'll see what that how that is. Okay. So start thinking about your final projects. And so if you already have an idea of what topic you want to do, maybe gather some friends together and try to get everyone to agree on that topic. And then let me know as soon as possible. So kind of the sooner you let me know what your topic is, the sooner I'm more likely to give it to you. Because I've had times in the past where multiple teams want to do the same topic, and so kind of the sooner I'm kind of just doing a first come first serve basis. And so the sooner you can decide, the sooner you can let me know, the sooner I can reserve it for you to make sure other groups don't take it as well. Okay. All right, so thank you guys for coming today. I hope you guys enjoy your weekend, and I will see you guys next week. Oh, and if you haven't picked up your exam yet, I brought the exams today as well.
I was doing the homework.
Yep.
And the number 3 has like the MATLAB question.
Yep.
And so when I run this, when I run the plot or whatever, it gives me the correct like first figure, but the second one, it's like, is it because I messed up the RY? Okay, so yeah, it's basically like both of them are, but in the answer, it's giving the.
Yeah, so one you have to multiply by. I think you have to multiply by -1.
Oh.
Let me once you send me this an email, and then I'll take a look today.
Okay.
I'll take a look during office hours, and I'll let you know.
Okay.
Yeah. Yeah. So the step length is just one step. Stride is kind of one full 2 steps, basically. Yeah.
So for finding the running speed, you have to use stride length, right?
So you can use stride length if you have the stride frequency. Yeah. And so, but to go from one to the other, one you just have to multiply by 2.
Thank you.
Yep.
You can have office hours.
Yes. Oh, sorry. Okay. Yeah. Let me. I'll meet you up there in a bit.